Okay, so the waiting time to success. It's very similar to the binomial where you try something n times. Now you're trying with success probability p, and you keep trying until you succeed. Okay, and the quantity that we're interested in, x, is the number of trials till the first success. Okay, and we did the PDF of x last time, so I'll just remind you what it was. So x, the possible values for the waiting time, how long you might wait, are 1, 2, 3, 4, 5, 6, and so on. And the probability to wait that long, okay, is beta times 1 minus p, beta times 1 minus p squared, beta 1 minus p cubed, beta 1 minus p to the fourth, and so on. Okay, where beta is equal to p over 1 minus p. It's just a constant. Okay, so we take the expected value using the formula. So the expected waiting time. So the expected waiting time. So how long you expect to wait until you succeed is equal to the expected value of x. Okay, we wait 1 times beta 1 minus p is equal to 1 times beta 1 minus p plus 2 times beta 1 minus p squared. 2 times beta 1 minus p squared plus 3 times beta 1 minus p cubed plus 4 times beta 1 minus p to the fourth plus da 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 and so on. Okay, so let's simplify this. So again, we have a sum. It's a complicated sum. We have to do this sum. Now the result is not going to be so intuitive. It's not hard, it's not easy to guess. So we really have to rely on the mathematics. Okay, so this is equal to, I'll pull out the beta. So it's beta, okay, and times 1 times 1 minus p plus 2 times 1 minus p squared plus 3 times 1 minus p cubed plus 4 times 1 minus p to the fourth plus and so on. So it's an infinite sum. Okay. So it's almost an infinite geometric progression, if not for the 1, 2, 3, 4, and so on. And you know, from the example with the binomial, you might think, oh, should I be taking a derivative and so on and so forth? So yes, you can use that same derivative trick that we used for the binomial, but I'll show you another trick. Okay. So let's compute the following sum. Okay. So in general, the sum is that we're interested in is 1 times a plus 2 times a squared plus 3 times a cubed plus 4 times a to the fourth plus and so on, where a, in our case, a is 1 minus p, but let's just compute it for a general a which is smaller than 1, positive but smaller than 1, so that this series converges. Okay, and so this is one of the standard things we do with geometric series. We multiply by the common ratio, so a times s is equal to 1 times a squared plus 2 times a cubed plus 3 times a to the fourth plus 4 times a to the 5 plus and so on. And what you'll notice is that you see here I have a squared, 2a squareds minus an a squared and an a squared, 3a squareds and 2a squareds, 4a fourths, 3a cubed and 2a cubed, 4a fourth and 3a fourth. There'll be 5a fifth and 4a fifth. So if I take s minus as, so s minus as is going to equal, well, a, okay, plus 2a squared minus 1a squared is just a squared, plus 3a cubed minus 2a cubed is just a cubed, plus 4a fourth minus 3a fourth is just a fourth, plus 5a fifth minus 4a fifth is just a to the fifth, plus da 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 da. And this is exactly the infinite geometric progression, except it doesn't start at 1, it starts at a. So this is a well-known sum. This is equal to a over 1 minus a, and this is s times 1 minus a. So if we solve for s, we get that s is equal to a over 1 minus a squared. Okay, so a useful little, formula for you guys who love formulas to stick away and tuck it away. You never know when you'll need a formula of this infinite sum. Okay, it's not quite the infinite geometric progression. It's weighted by 1, 2, 3, and so on. Okay, now in our example, a is 1 minus p. So the expected value of x is equal to beta, which is p over 1 minus p. So p over 1 minus p times, okay, this sum which we just computed. So we have a, which is 1 minus p, divided by 1 minus a squared. So 1 minus a is just p, so divided by p squared. So this is equal to the 1 minus p's cancel, one of these guys cancel, 1 over p. Wow! So the expected waiting time, even though it started with a very complicated summation formula, simplified very nicely to just 1 over p. So let's do an example. Okay? So let us say that you are having kids, okay, until you have a boy. Okay. Well, if the probability of a boy or a girl is, 1/2, then you will say that, the chances are 1/2 of success. And you keep doing this until you succeed. Succeed means have a boy. Okay. So the expected waiting time is 1 over the probability of success, 1 over 1/2. So waiting time to boy is equal to 1 over p, which is 1/2, which is 2. So you expect to have 2 kids. What about the waiting time to a girl? It's also 1 over 1/2, which is 2. Now, supposing on Mars, boys and girls are not equally likely. So girls are more likely and boys are less likely. So let's say that, the chances of a girl are 2/3. Probability of a girl is equal to 2 over 3. Probability of a boy will then equal 1 over 3. Now the waiting time for a boy is 3 on average. You expect to wait 3 children to get a boy, your first boy, and the waiting time for girl is equal to 1 over this, which is 1.5. Okay, so you expect to have 1.5 children on Mars before you have a girl. So I don't know what it means to have 1.5 children. Can someone tell me? Waiting 1, 2, 3, 4, 5. Yes! If what you said is no, this is not the number of children you have to have. This is the number of times on average you would wait if you did this experiment many times. So if 1 million people had children and then they looked to see, how many children did they have till they got their first girl? Some of them would have 1 child, it would be a girl. Some of them would start with a boy and then a girl, so 2 children and so on. Okay? And when you compute the average number of children that you need to wait in order to get a girl, it's 1.5. I don't know anyone who can have 1.5 children. Okay? So it's important to understand what the expected value means. All right. Okay. So now I'm going to tell you about the conditional expectation. So we've done expected value. Okay, and we have, taken a look at lots of examples. Okay, and just like, if you're doing an experiment, okay, and you're computing a probability, but if you get new information, you change the probability. And it's the same with expected values, because an expected value is just a summary of the experiment. Okay? So if I give you new information, you're going to update your expected value. We call that conditional expectation. Okay, and so we'll start with an example, and then we'll define it, and then that'll lead us to the law of total expectation, just like the law of total probability. And I'll show you a nice application of the law of total probability to waiting times. Okay.